Typhoon Fong Wong just struck the Philippines with 185 km/h winds, and scientists are terrified by what they found.
It's the second major typhoon to strike the country following Typhoon Kalmagi, which left a trail of destruction, and as you say, killing more than 200 people.
Because this monster storm is breaking every rule in the meteorological playbook. Picture a typhoon so massive it covers 2/3 of an entire country, packing winds of 230 km/h that triggered the Philippines' highest possible warning level, signal number 5, reserved for catastrophic destruction. Over 1 million people have been evacuated as this beast made landfall in Aurora province, already claiming 2 lives and turning entire regions into disaster zones. But here's what has weather experts completely stunned. Fong Wong's wind and rain bands are impossibly wide, stretching across distances that should be physically impossible for a single storm system. Satellite imagery shows a perfectly organized eye wall that is maintaining its structure despite hitting mountainous terrain that should tear any normal typhoon apart. Even more bizarre, the storm is generating storm surge and flooding patterns that do not match its official category, as if it is drawing power from sources meteorologists cannot identify. Emergency teams are bracing for impacts that exceed their worst-case scenarios. This is the environment into which Typhoon Fong Wong arrived, not as an isolated monster, but as the latest and most extreme entry in a long, accelerating series of storms. For the people of the Philippines, the threat is never abstract. It is woven into daily life, shaping everything from school calendars to the design of homes. Each storm tests the limits of preparation, and each year, those limits are pushed a little further. Meteorologists in the Philippines depend on a web of sensors and cross-checks to keep the country one step ahead of disaster. Every tropical cyclone is tracked by a combination of land-based weather stations, Doppler radar, satellites, and coastal buoys. Each system provides a different piece of the puzzle: surface winds, rainfall, pressure, and the shifting shape of the storm itself. PAGASA, the Philippine Atmospheric, Geophysical, and Astronomical Services Administration, has strict protocols. No single reading is ever trusted alone.
Here's the wind animation for you, so we'll click now. Areas where it's purple going towards white, that's where you're talking about those really damaging winds. The timestamp.
Satellite images are compared with radar scans, and both are checked against the real-time numbers coming in from ground stations. If one sensor goes down, another is supposed to fill the gap. Redundancy is not just best practice, it is the only way to catch sudden changes that could mean the difference between a safe evacuation and a tragedy. Analysts work in 30-minute windows, layering new data over the last, hunting for discrepancies. If 2 sources disagree by more than a few percent, the team pauses to investigate before issuing an alert. For a major upgrade, like raising the wind signal to the highest level, confirmation from at least 2 independent sensor types is required. Manual review by senior forecasters is mandatory when the network is degraded or readings seem off. This rigorous multi-layered approach was stress-tested just days before Fong Wong, when Typhoon Kalmagi battered Luzon and knocked out several key stations. The strain left gaps that would haunt forecasters as the next storm gathered strength offshore. In a region where every minute counts, the reliability of this network shapes not just forecasts, but the fate of millions. At 3:40 in the afternoon, the first crackle of the municipal loudspeakers echoed through Dinalungan's narrow streets. Mayor Joel Batong stood shoulder to shoulder with his disaster council, his voice steady, but his eyes betraying the pressure. The latest PAGASA bulletin had just upgraded the alert to signal number 4. With winds already tearing at roofs along the coast, there was no time to debate. Within minutes, police and barangay officials fanned out, knocking on doors and urging families to leave everything behind. Some clung to their homes, unwilling to abandon animals or precious belongings. The mayor's order was clear. If persuasion failed, forced removal would follow. He told his team, "No rescue once the winds begin," repeating the line that had become a grim refrain. 6 hours before landfall, evacuation centers filled with the sound of crying children and hurried prayers. Field teams relayed updates over handheld radios, voices sometimes lost in static as the first gusts snapped power lines. Generators hummed to life in the municipal hall, the only place with steady light. Batong's phone rang non-stop with calls from regional officials, desperate parents, and his own wife asking if he was safe. With the main radio tower threatened by flying debris, backup frequencies were activated, and runners were sent between checkpoints with written orders. When the first reports of flooding came from the riverbanks, the mayor faced an impossible choice: send teams out into the teeth of the storm, or wait and risk losing track of those left behind. He chose caution, locking down the coastal perimeter and halting all travel. Later, as news of 2 deaths filtered in, one a drowning and the other a roof collapse, Batong's frustration was raw. He said they had done everything humanly possible, that their town was evacuated before the typhoon arrived, but nature's force was beyond prediction. The unfortunate deaths happened when townspeople tried to go back for their things, not realizing the surge would hit so fast. In the end, every minute counted, and every decision weighed on his conscience. 90 minutes after midnight, a desperate voice crackled through the static. Fishermen aboard the San Lorenzo, 3 kilometers off Casiguran, were losing power fast. Their engine was dead, the auxiliary generator already drowned by the rising sea, and waves were now cresting over 8 meters. The crew's radio plea came in broken bursts. "We're adrift, hull taking water, anyone please." The Philippine Coast Guard cutter, Bagong Bayani, was already fighting its own battle. The blackout had swallowed the coastline, and only the faint pulse of emergency beacons cut through the rain. Every navigation system flickered between error codes. Still, the captain pressed on, steering by memory and instinct, as wind gusts slammed the vessel broadside. The deck pitched violently, sending equipment skidding and forcing the rescue crew to lash themselves to the rails. Visibility dropped to near zero. Searchlights bounced off walls of spray, revealing nothing but chaos. The crew relied on handheld radios, voices trembling as they tried to triangulate the San Lorenzo's last known position. A rescue rope was fired across the gap, but it snapped in an instant, lost to the churning dark. On the open channel, a Coast Guard officer's voice broke through. "I can't see the hull. God help us, we're drifting." For an hour and a half, the Bagong Bayani circled blind, engines straining against the current, every minute stretching the line between hope and disaster. Lightning lit the faces in a fisherman's cell phone video, hands white-knuckled on the rails as the cutter finally loomed out of the storm. The crew hauled the survivors one by one over the side, shivering and silent as the wind screamed on. The rescue ended with all hands saved, but the sea had nearly claimed them. On shore, no one could explain how the cutter found its mark in that darkness. Only that the rules of survival, like the rules of the storm, had been rewritten that night. As dawn broke over Luzon, the world's most advanced satellites locked onto Typhoon Fong Wong. From space, the storm looked almost unreal, a perfect spiral, with the eye wall unbroken and a cloud shield stretching so wide that meteorologists at the Joint Typhoon Warning Center started to question their own models. Himawari 9's infrared scans suggested a storm diameter approaching 1,400 kilometers, while Pegasus' Doppler radar, when it was online, tracked bands that seemed to reach from the Pacific coastline all the way to the Western Plains. But as the data poured in, the numbers refused to settle. Some satellite windfield estimates hinted at a system far larger than anything in the books, while ground stations, where they survived the onslaught, reported wind speeds that fit more typical super typhoon profiles. Inside the forecasting rooms, a quiet debate turned fierce. Pegasus' lead analyst stuck to the agency's protocols, insisting on a storm size just within the upper limits of known Pacific typhoons. Across the ocean, Joint Typhoon Warning Center forecasters circulated a leaked message stating that this defies the known physics of band formation. The phrase bounced through meteorological forums, fueling a rush of speculation. Was Phong Wong a single massive engine? Or was something stranger at play, a multi-vortex structure hidden beneath the swirling clouds? The science was not just academic. Windfield diameter determines who gets warned, who evacuates, and where resources are sent. Pegasus' conservative estimate meant some regions stayed on lower alert, while the Joint Typhoon Warning Center's more aggressive modeling triggered warnings across an area almost the size of Western Europe. The clash between pixels and physics left emergency planners in limbo, forced to choose between conflicting projections as the storm bore down. In the end, every decision hinged not just on what the instruments saw, but on how much uncertainty the scientists were willing to risk. In the hours after landfall, coastal engineers began the grim task of measuring what the models had missed. In Baylor, Aurora, tide gauges and port cameras recorded water climbing to 3.5 meters, sometimes even 4 meters, swamping the river mouth and pushing more than 200 meters inland. That surge, nearly 1 meter higher than official forecasts, left entire barangays underwater long after the winds had eased. In Burdeos, Quezon, and Pandon, Camarines Norte, the story was the same. Watermarks on school walls and market stalls showed run-up levels that defied the guidance local leaders had relied on. In Virac, peak surge reached 3.5 meters, flooding the port and sweeping debris deep into town. While in Pandan, the sea pushed farther inland than any living resident could recall, engineers tracing the disaster point to the way Phong Wong's massive windfield and the unique shape of local bays combined to focus the surge. In Baylor Bay, the coastline bends into a natural funnel, amplifying the force of water driven by hours of unbroken onshore wind. At the same time, torrential rain from the mountains poured down swollen rivers, meeting the rising sea at exactly the wrong moment, high tide. The result was a compound flood, overwhelming defenses designed for smaller, slower surges. In some places, the water continued to rise even after the storm's eye had passed, catching families who thought the danger had ended. Post-storm surveys confirmed the models had underestimated not just the height of the surge, but how far it would spread. Engineers found that outdated maps and incomplete data on river mouths and sandbars had left blind spots in the forecasts. In Baylor, the difference between predicted and observed surge meant hundreds more homes flooded. In Virac, emergency plans based on lower numbers fell short. For coastal scientists and engineers, these failures are more than academic. They are a call for urgent fixes, better data, and models that can keep up with storms that refuse to follow the rules. But here's what's really chilling. The storm surge wasn't the only thing that exceeded predictions. The rainfall patterns across Luzon showed something meteorologists are still struggling to explain. Stations in the Sierra Madre Mountains recorded over 500 millimeters of rain in 24 hours, numbers that match the most extreme tropical cyclone rainfall events ever documented in the Philippines. But what has experts puzzled is how that rain was distributed. Normal typhoons, even super typhoons, tend to drop their heaviest rainfall in a concentrated band around the eye wall, with totals decreasing as you move away from the center. Phong Wong did something different. Rain bands hundreds of kilometers from the center were producing rainfall intensities that matched those near the eye itself. It's as if the storm had multiple centers, each generating its own deluge. River systems across Aurora, Nueva Ecija, and Isabela reached flood stages, normally associated with storms twice Phong Wong's official size. The Cagayan River, one of the longest in the Philippines, swelled to levels not seen since Typhoon Haima in 2016, despite Phong Wong's track staying well to the south. Flash floods struck communities that had never been in any typhoon's direct path, catching residents completely off guard. Hydrologists reviewing the data are now questioning whether the wind field estimates were too conservative. Dr. Maria Santos, a researcher at the Manila Observatory, told colleagues in a confidential briefing that the precipitation footprint suggests we're dealing with a storm system whose effective size was far larger than any satellite-based measurement indicated. If true, it means thousands of people were living inside a danger zone without knowing it, protected only by luck and not by science. In the chaos of Phong Wong's landfall, the country's warning system cracked open. As the storm battered Aurora and Bela, the Bela Doppler radar, crucial for tracking rainfall and wind direction, went dark for nearly 18 hours. 4 coastal tide gauges, including those in Bela, Casiguran, Apari, and Infanta, dropped offline just as the water began its deadly climb. 3 weather stations in eastern Luzon lost full data feeds for over half a day, leaving meteorologists with only scattered readings as communities face the surge. In hard-hit barangays, the absence of live sensor data meant flood warnings lagged by an hour or more. Emergency managers later admitted that situational awareness was severely degraded at the worst possible moment. The equipment failures weren't random. They followed a pattern that revealed a disturbing vulnerability in the nation's disaster infrastructure. Many of the sensors that went offline were older models, installed a decade or more ago, already operating beyond their designed lifespan. When Typhoon Kalmegi swept through just days earlier, it had damaged several stations that hadn't been fully repaired by the time Phong Wong arrived. Budget constraints meant replacement parts were delayed, and backup systems in some locations simply didn't exist. Relief logistics faced their own ordeal. The Department of Social Welfare and Development had prepositioned a record 2.04 million family food packs across Luzon and the Visayas. But as evacuation numbers soared past projections, local hubs in Aurora and Isabela found their stocks running thin. Blocked roads and closed ports left entire towns waiting, sometimes for days, as supplies sat out of reach in regional warehouses. Humanitarian trackers flagged the gap. Record stockpiles on paper, but distribution paralyzed by impassable routes and missing real-time data on which communities were cut off. Mitzi Jonel Tan, a leading climate activist, voiced the frustration of many. She said, "People keep hearing about investments in disaster response, but the sensors are old, the networks are fragile, and last-mile delivery breaks down when it matters most." She warned that the government needs to treat science and adaptation as survival, not an afterthought. For millions, the storm, exposed how quickly even the best-laid plans can unravel when key links in the warning chain fail. But the equipment failures and logistical breakdowns were symptoms of a deeper problem, one that scientists are only now beginning to confront. 5 signals now stand out, each one pointing to a storm era that refuses to obey old limits. First, the Western Pacific sea surface temperature anomaly reached plus 1.2 degrees Celsius this season, enough extra heat to supercharge any cyclone that forms. Ocean heat content east of Luzon was also at record highs, giving Phong Wong a vast reservoir of energy even as it crossed land. The Madden-Julian Oscillation, a global pulse of tropical thunderstorm activity, arrived in phase with the storm's birth, stacking the odds for rapid intensification. Atmospheric moisture was off the charts, with a persistent trough drawing deep water vapor across the West Pacific. At the same time, vertical wind shear, normally a typhoon's enemy, remained unusually weak, allowing Phong Wong to keep its symmetry and strength when most storms would unravel. Each of these factors alone is a red flag. Together, they create a recipe for extremes that cannot be explained by luck or chance. Dr. Ronald Villarin, an atmospheric scientist at the University of the Philippines, put it plainly: this is not just a one-off event. The storm structure and energy profile suggest we are entering an era when the bounds of cyclone behavior are shifting. But here's what has climate scientists really worried. Phong Wong is not an outlier. It's part of a pattern. Over the past 5 years, the Western Pacific has produced a string of storms that have pushed, and in some cases broken, records for intensity, size, and rainfall. Typhoon Haiyan in 2013 set the bar with wind speeds that reached 315 kilometers per hour at landfall. Typhoon Goni in 2020 matched that intensity. Typhoon Rai in 2021 devastated the Visayas with a combination of extreme winds and storm surge that caught even experienced disaster managers off guard. Each of these storms forced scientists to recalibrate what they thought was possible. Each one revealed gaps in forecasting models and weaknesses in warning systems. And each one, including Phong Wong, carries the fingerprint of a warming climate. Warmer ocean temperatures providing more energy, higher atmospheric moisture content, feeding heavier rainfall, and changing wind patterns altering storm tracks in ways that are only now becoming clear. The implications are staggering. If Phong Wong represents a new normal, then the infrastructure designed to protect millions of Filipinos, the seawalls, the evacuation centers, the early warning systems, is already obsolete. The question is not whether another Phong Wong will strike, but when, and whether the country will be ready. For scientists like Dr. Villarin, these signals are not just warnings. They are evidence. The future is no longer about the storms we remember. It is about monsters we have yet to imagine. And the terrifying reality is that the tools we have to predict and prepare for these storms are struggling to keep pace with how fast the climate is changing. In the aftermath of Phong Wong, as communities begin the slow work of rebuilding, scientists are racing to understand what made this storm so different. Preliminary analysis suggests that the storm's unusually large wind field may have been the result of a rare atmospheric configuration, one where multiple sources of energy fed into the system simultaneously, but confirming that hypothesis will require months of detailed analysis, combing through terabytes of satellite data, radar scans, and ground observations. And even then, the answers may raise more questions than they resolve. Because the uncomfortable truth is that our understanding of tropical cyclones, built on decades of observation and theory, may no longer be adequate for the storms that are forming. Now, some researchers are calling for a complete overhaul of how typhoons are categorized. The Saffir-Simpson scale, which ranks hurricanes and typhoons based on wind speed alone, fails to capture the full threat posed by storms like Fong Wong. Storm surge, rainfall, and size are equally important, yet they're often treated as secondary considerations. A storm with lower wind speeds but a massive wind field and extreme rainfall can be far more destructive than a compact Category 5 system. There's also growing concern that the models used to predict storm intensity and track are based on historical data that may no longer be relevant. If the baseline climate has shifted, then using the past to predict the future becomes increasingly unreliable. Some forecasters are advocating for the use of artificial intelligence and machine learning to identify patterns and relationships that traditional models might miss. But technology alone won't solve the problem. The human element, the decisions made by local officials, the trust communities place in warnings, the willingness of people to evacuate when told, remains as critical as ever. And that trust is fragile. When warnings prove too conservative, as they did with Fong Wong's storm surge, people may ignore future alerts. When evacuations are ordered, but the worst doesn't materialize, fatigue sets in. Today, as evacuation centers fill and meteorologists scramble for answers, the Philippines faces storms that defy prediction and preparation. Fong Wong's unprecedented power exposes how climate extremes now outpace our models and our response. The warning is clear. Nature's new playbook is already being written. Are we ready to read it and act before the next page turns? For the families who lost loved ones, for the communities still underwater, for the scientists staring at data they can't fully explain, the answer is far from certain. What is certain is that Typhoon Fong Wong will not be the last of its kind, and the next one could be even worse.